Hello and welcome to All Mass Considered. In this video, we will look at rotations in the plane through the prism of matrices. We shall see how they can be represented as matrices and how composition of rotations, which is of course a rotation itself, can be viewed as a matrix multiplication. This way, rotations in the plane will serve us as a good example, which illustrates some facts which are true in linear algebra in general. Our basic but fundamental observation is that a rotation is a linear transformation. So let us recall what this means. So let F denote a rotation. So it's a rotation of the plane counterclockwise with an angle phi. F linear means the following. If we have a vector v, then f of alpha v is equal to alpha f of v, where alpha is any number. This is clear because multiplying by the number alpha just means that we are scaling the vector, possibly changing its direction if alpha is negative. Clearly, it is the same to scale the vector first and then to rotate it, or first rotate it and scale it by the same factor. That's the first property. The second property of linearity is that for any two vectors v and w, f of v plus w is equal to f of v plus f of w. For rotations, this just means that if we have two vectors, then we can first sum them and then rotate, or first rotate them individually and then sum them. The result will be the same. These two properties together mean that a function is linear. So one of the fundamental concepts of the linear algebra is the correspondence between linear maps or linear transformations and matrices. Let us see how this correspondence works in the case of rotations. Before we do that, let us recall the definition of sine and cosine. So let us consider a unit circle, and let us consider a vector with angle phi. Then this is a unit circle. Then the coordinates of this vector, by definition, are cosine of phi and sine of phi. This is usually the definition of cosine and sine, taking the unit vector with angle phi and taking its x and y coordinate. So let E1 and E2 denote the unit vectors. So E1 has coordinates 1, 0, E2 has coordinate 0, 1. Using the sine and cosine terminology, we can describe what happens with the vectors E1 and E2 under the rotation. Again, remember our rotation is counterclockwise angle phi. F of E1 will be precisely this vector which we have drawn here. This will be the vector with coordinates cosine and sine. Let me write this on top of each other for later multiplication. So this will be the vector cosine, sine. Similarly, the image of E2 will be the vector which I can draw here. This is the angle which will be phi. Its coordinates will be similar to f of E1, with the only difference that we need to change them. We need to swap them and change the sign. So the first coordinate of that vector will be minus sine phi, and the second coordinate will be cosine phi. The coordinates of these rotated vectors just can be seen geometrically and using the definition of cosine and sine. What about the coordinates of other rotated vectors? Let's say I want to rotate the vector v 1, 2. To do that, I can write v as a linear combination on standard basis. This is 1 times E1 plus 2 times E2. This is by definition because the coordinates are 1 and 2. Now, if I want to rotate it, since I know that the rotation is linear, f of E1 plus 2E2 will be the same as f of E1 plus 2f of E2. In general, if you have any vector with coordinates a, b, and rotate it, we will obtain the vector a f of E1 plus b f of E2. Now, if we recall the definition of the matrix multiplication, we will see that this is precisely the same as taking the matrix with the first column f of E1 and the second column f of E2. This is a 2 by 2 matrix, and multiplying it by the matrix AB. This equality is due to our definition of the matrix multiplication. So if we now simply take the matrix A, f of E1, f of E2, then the rotation will be described for any vector. F of any vector, AB, will be simply A times AB. And we know what this matrix is, because we know what f of E1 is and what f of E2 is. This matrix is cosine phi minus sine phi, cosine phi. So we have a matrix A representing our rotation. So from what we just said, we can derive a formula for the rotation of a vector. So if we have vector AB, to rotate it, we just multiply it by the matrix cosine phi minus sine phi, cosine phi, multiplied by AB, and we will get a formula A cosine phi minus B sine phi, A sine phi plus B cosine phi. So examples. Take phi equal to pi half. Then the cosine of pi half is equal to 0. And the sine of pi half is equal to 1. So the formula will say that the vector AB will be rotated to the vector minus BA. This is the orthogonal vector. And the rotation is counterclockwise. As another example, if we take phi equal to pi, then the cosine of pi is minus 1. Sine of pi is 0. So the vector AB will be rotated to the vector minus A minus B. This is, of course, also what's called central symmetry, where every vector is mapped to minus itself. If you also know the complex numbers, you can confirm the formula star by complex multiplication, because in complex numbers, the vector AB will be A plus IB. A is the real part, B is the imaginary part. And to rotate, you will have to multiply it by the unit length vector cosine phi plus I sine phi. This is a complex number which corresponds to the unit vector with angle phi from the x-axis. So using the rules of complex multiplication, we first calculate the real part. The real part will be A cosine phi minus B sine phi, because we have I square, plus the imaginary part will be I times B cosine phi plus A sine phi. You see that we get the same as on the right-hand side of the star formula. As a last note, remember that in linear algebra, not only linear transformations are encoded by the matrices, but also the composition of the linear transformations is encoded by matrix multiplication. So the composition should correspond to matrix multiplication. So let us compose two rotations, one by angle alpha and the other by angle beta. They will correspond to two matrices, so the rotation by angle alpha will be encoded by the matrix cosine alpha minus sine alpha, cosine alpha. And if we want to compose it with the rotation by the angle beta, we'll have cosine beta minus sine beta, cosine beta. And let us multiply these two matrices. By the rules of the matrix multiplication, we will obtain a matrix. Here we have to do cosine alpha minus sine alpha times cosine beta sine beta. So we'll have cosine alpha cosine beta minus sine alpha sine beta. Below it we'll have sine alpha cosine beta plus cosine alpha sine beta. Here we'll have minus cosine alpha sine beta minus sine alpha cosine beta. And finally here we'll have minus sine alpha sine beta plus cosine alpha cosine beta. And this matrix is precisely equal, if you remember the cosine formula, precisely the cosine alpha plus beta sine alpha plus beta. And here, of course, minus sine alpha plus beta, and here cosine alpha plus beta. So we see the connection here. The matrix multiplication for these matrices corresponds to the matrix of the rotation by the angle alpha plus beta, which is exactly what happens geometrically if you first rotate by alpha and then by beta. So to summarize, we could see on this example of 2 by 2 matrices how the geometric rotations correspond to matrices. Since they are linear transformations, they can be represented by matrices. The matrices are skew-symmetric. Cosinus phi minus sinus phi in the first row, sinus phi, cosinus phi in the second row. These matrices encode rotations. Multiplying vectors by these matrices give you formula for rotation of these vectors. Multiplying these matrices with each other gives you a formula for cosine and sine of the sum. And you can also see that if you know the complex multiplication, you see that this matrix multiplication of these matrices corresponds to the complex multiplication of complex numbers, where the rotation by angle phi corresponds to multiplying by the complex number cosine phi plus I sine phi. And you see here again as a central concept that if you want to encode a geometric transformation, a linear transformation by a matrix, what you need to do is to see what are the images of the unit base vector, and you have to make up a matrix where the images are columns in this matrix. This is exactly what happens here. We form this matrix cosine phi minus sine phi, cosine phi, by putting as a first column cosine phi, sine phi, the image of the first unit base vector, and as the second column minus sine phi, cosine phi is image of the second vector in this standard basis. So this is a connection between rotations in the plane and 2 by 2 matrices with cosine and sine.